Welcome everybody to this talk about reinventing Qt core for Qt6. As I said in my keynote presentation earlier, Qt6 has been a lot about going back to the basics, to the core of Qt and looking at our fundamental architectures, changing things that we cannot change when we do minor version updates. In Qt6, we've been doing a lot of work now, looking at those things, and that meant for us to going back to the core libraries, to Qt core, and seeing what we want to change there and how to do that. Let's start off with our templates and container classes. On the container side, we've done a lot of work trying to close the API gaps towards the STL containers, have support for move operations, for all the things that you get in modern C++, emplace, initializer lists, and other things. We've also removed the 2 GB size limitations that we had in the containers in Qt 5 by using QSize type consistently, which expands to a 64-bit integer on 64-bit systems. And we've done some work making sure that default constructors are not const expressions and non-allocating, so that they can fit better into your source code and really don't do anything when you construct them. QList and QVector has been a big area to work with that also sparked a lot of discussions internally. How do we solve this? What do we want to do with it? We've had those two classes in Qt 5 as separate classes. QVector being similar to standard vector, just a linear storage container. QList having a bit of let's say, interesting data structure in that it changed depending on what you put into it. In Qt6, we've gone back and we said, let's simplify this. We have only one class and make QList being the default name for it, and QVector is now an alias to QList. This actually simplifies our API and simplifies also how you can use those classes. We've removed some of the performance issues that we had with QList in Qt 5 using a vector-based data structure, and when we did the measurements, this improves performance in pretty much all cases that we've measured. It's also 100%, almost 100% source compatible. There's one exception that in QList in Qt 5, when you had large objects stored in there, you could keep references to these stored items and they would be stable under modification of the QList. That's not the case in Qt6 anymore, and something you should be aware of. QMap and QHash as the other two container classes that are used a lot also received a lot of attention. In Qt 5, they were a combination that QHash actually and QMap could store multiple entries with the same key. We've done changes to that, and in Qt6 they are separated fully. So you have a QHash and a multi-hash to store multiple entries. QMap and QMultimap, the same thing. And they don't inherit from each other anymore. QMap we have implemented now on top of standard map with an added implicit sharing and ref counting. So that also means that you can easily move a standard map to a QMap and move from a QMap to a standard map. It's a very nice addition and improves the compatibility also with the standard containers. For QHash, we've gone a little bit a different route and went towards our own implementation. The reason for that will become a little bit clearer when we look at some benchmarking data later on. Our implementation now uses open addressing, and it's very fast and has a very low memory usage. Let's have a look at the internals there and how this has been implemented. QHash basically has a pointer to some data, and that data basically then contains the size of the hash, the number of available buckets right now, and a pointer to a list of spans. Those spans can contain each 128 buckets, or each contain 128 buckets, and up to 128 allocated entries in there. So we have inside the span a small data structure of 128 bytes large that contains offsets into an entry array, which tells you that for each bucket that we have in the hash, where to find the entry, if one exists. And then you also there have an additional 2 bytes for telling you how much you have allocated, and a free list when things get removed from the hash so that we can reuse those nodes. An entry is then simply a union of a node. It can either be a node or an entry in the free list. And the node, of course, is just a key and a value pair. That allows us to actually implement a hash that has a pretty high performance, very high performed hash table with a very low memory overhead. If we go to the next slide, we can see a little bit how that works out and the performance numbers here. Let's focus on this on the graph on the left first. The red line is what we had with QHash in Qt6. It's normal. It's an average benchmark over insertions, removals, iterations, and a couple of other operations that we've been testing there. It's normalized to 1 for a small QHash of 1,000 entries, and then you see how they scale against each other. The green line is QHash in Qt6, and you can see that we're actually, for large hashes, more than a factor of 2 faster on average across all of those operations. And a lot faster also than standard hash, which has pretty much the same performance as QHash, or standard unordered map, to be exact. In terms of memory consumption, we are also seeing that we are much better. So the right-hand graph shows you, for hash tables between 10,000 and 10 million entries, the average memory that's being used per entry in the hash table. And you can see that QHash in Qt6 was using a lot of memory. For a hash table with int64 versus mapping to int64, which has a basic memory overhead, memory usage of 16 bytes per entry and then some overhead. We were actually using 60 bytes. QHash in Qt6 is much, much more conservative in terms of memory usage. It only has around 8 bytes of overhead per node in the entry. You may also wonder a little bit about the blue line, which is TSL sparse map, a very high performant and low memory usage hash table implementation. That's consistently somewhat better than QHash, but it had other problems. That's why we couldn't use that implementation directly. For example, it wasn't 100% stable against repeated inserts and removes into the hash table. If you do that for a very long time, performance would degrade and you would get some other problems. We've solved those with QHash and still keeping the performance at pretty much the same level as the TSL hash sparse map. Let's move on then to the next topic, Unicode and text handling. In Qt6, we've changed a lot of things and assume that all text handling is Unicode based. UTF-16 is the default string encoding that we're using internally for storing string data and text data. The default on-disk storage format is UTF-8, and that's how we handle everything. We also assume that source code is UTF-8. So if you have a simple quoted 8-bit string in your source code, we will treat it as UTF-8 by default. The string classes have undergone some cleanups, making the usage more clear and having a more consistent set now. So we have a qbyte array that's nowadays in Qt6 ASCII only, not Latin 1, because Latin 1 would conflict with our UTF-8 handling as a different encoding. We have a QUTF-8 string view class introduced as a wrapper to tag 8-bit string data as UTF-8. We've completed the QStringView API so that you can use all the const non-modifying QString API also simply as view onto data. And we've added also view APIs for qbyte array and as well, so you have a qbyte array view. Finally, we removed the old QStringRef class, which was basically filling the same purpose as QStringView with a more older API and something, an architecture that was not quite what we wanted to have for the future. Still, QStringView can pretty much serve as a drop-in replacement for StringRef, and StringRef is available in the compat library if you still need it. Regular expressions is the next topic that we're having. We've had in Qt5 two regular expression engines that we've been working with. We've had QRegExp as the class that we have had since Qt2, Qt3 times, and QRegular expression as the new class. With Qt6, we've now done the transition and moved QRegExp out of the core library into a compat library. It's still available there, but everything else is QRegular expression based. Porting from QRegExp to QRegular expression is relatively straightforward, so if you want to get rid of QRegExp, this is now a good time. We've been also working on text conversions as the next topic. So the Qt text codec API has been removed from Qt core. It's still available in the Qt5 compat library, so if you rely on it, you can still use it. But we didn't want to have it in Qt core anymore because it didn't fit together with our Unicode everywhere handling that we want to have now moving forward into the future. But we have added a new, more modern API with QString encoder and decoder. The API is now value-based, not pointer-based, and it's by default stateful. And it supports UTF-8, UTF-16, UTF-32, Latin 1, and local 8-bit encodings. It is in the future extensible to support full code conversions with also legacy encodings after 6.0 if there is a need. Let's move over from now those text handling container classes over to one of the big new topics, and that's properties and bindings. Properties and bindings has been a concept that we've introduced, or bindings has been a concept that we've introduced with Qt5 and with Qt Quick. Here you see a small snippet of Qt Quick code, basically showing you a rectangle where we have two bindings. One where we bind the height of the rectangle to the width, so we keep it always square. And another one where we say, okay, the border should be 1/10 of the height. In Qt Quick, the engine that we have developed there made sure that those relationships always held true, and the binding basically updated the properties on the left-hand side automatically when the width or the height changed. Now our goal was to translate that into into C++, make that available in Qt core and for all of Qt. This is how, our first sort of idea was how an API like that could look like. You have a struct rectangle. You have three properties in there of ints, width, height, and border, and a constructor which sets up the bindings where you say height.set binding to the width, and border already set the binding to a lambda which returns 1/10 of the height. So that was our goal, and let's see how that looked like and what kind of goals we there had. So we wanted to bring the best part of QML to all of Qt. Move the binding infrastructure into Qt core. So it's not a separate part and separate piece anymore like it was before. It was a separate large engine in the QML engine, or large part of the QML engine. Now it's in Qt core, and we want to make that available to everybody. We want to make sure that you can extend existing properties in QObjects with support for those bindings. You can add binding supports also to any other class if you wanted to do. So have properties that are bindable in any class. And we wanted to change a little bit how binding evaluation worked. In Qt5 that was done eagerly, so whenever a dependency that you had, so something that was mentioned on the right-hand side of the binding, changed, the binding got immediately re-evaluated. That often led to bindings being re-evaluated multiple times and more often than they needed to, which was a performance problem, especially in larger scale projects. So we wanted to make that lazy. only mark a binding as dirty if something changed, and then we evaluate only when the value is required. And with that also make it fast. So how does this turn out? Well, here's how the API that we have now in Qt6 looks like. You can implement your own class rectangle, and you can have Q properties of int, width, height, border, and in the rectangle constructor, you see that there's slight differences now. You set the binding, and you have to, if you want to just bind one property to another, you have to use this Qt property binding method that returns you a binding on an existing property. If you're using lambdas and functions, that actually looks pretty much exactly as we originally thought we could do it. So how is this all implemented? We have the class Q property, and what it has is basically has two things in there. First of all, it has the data, just whatever the template data is, and then it has a standard function to a binding, which is null by default. And that's now a very trivial implementation that you can see here. You know, what we do is, if you say, if you want to get the value of the property, if we have a binding, we evaluate the binding and return its result. Otherwise, we return the data. And in the set value call, if we have a binding, we reset it to and clear it and set the new value. And then we have a set binding function, which just sets the binding. Problem with this trivial design is that you would reevaluate that expression every time the value is being asked for. That's not very efficient, so we had to go and do a bit more work to make this work very nicely and fast. This is how the real thing now looks like, and it's getting a bit more complex, and I can't show you all the details. If you want to have a look at those, look at the source code in qproperty.h and qproperty.cpp in Qt6. But what we have here is now we have also again the value, and we have a property binding data that we're using. And then we check now if you ask for the value. If you have a binding, well, we'll reevaluate the binding if it's dirty. Second thing we need to do is we actually need to register with a currently evaluating binding. So if the value is being asked for inside a binding expression, we want to know that this binding expression actually requires this value, so we can mark that another binding dirty if this value is changing. In the set value, well, that looks actually a little bit similar. We remove the old binding, a pre-existing binding if there's one. Then we check if the value is the same as before and return, because we otherwise don't want to do the work afterwards. Otherwise, we assign the new value, and then we notify all bindings that have a dependency on this property that the value has changed and that they need to mark themselves as dirty. So that's what we could do and how we implemented the bindings using QProperty. Now, when we go over and look at QObject, things get a bit more complicated. And the reasons for that is that we have an existing property infrastructure in QObject, and we wanted to avoid breaking compatibility with Qt5. The existing infrastructure there is based on setter and getter methods. So we needed to find a way to extend the existing set property mechanism with bindings. We need to hide the data there because of compatibility between releases, and the data really lives in QObject private. It doesn't live in QObject itself for most of the things that we are doing in Qt. And we wanted to avoid both memory and runtime overhead if bindings aren't used. You saw in QProperty that every QProperty uses one additional pointer to store a pointer to the bindings. If the property system is not used, it would be nice to avoid that memory overhead. So what's the solution? Let's have a look. So the binding support is now a simple addition to the existing system. We're adding a getter for a binding interface that you can get. It's called QBindable of the property type of int, for example, bindable property. So you can actually access then with that all the binding properties inside for the property inside QObject. We extend the QProperty macro that we have with the bindable tag, which tells mock about the binding interface, so it can generate the introspection data for runtime introspection that we need. And then we use QObject bindable property, a macro, to implement the data storage. This macro only works as a member of, if you put it in as a member of QObject or QObject private. But it has the big advantage that with that we can reduce the memory overhead to pretty much nothing if bindings aren't used. All we need now is one additional pointer in QObject private, and if bindings aren't used, that's all there ever will be an additional memory overhead, and checking that one pointer is the only runtime overhead as well when you set or retrieve a property value. Here's how an implementation of a proper bindable property looks like now in a QObject subclass. You basically use, as always in as in Qt5, the QProperty macro to mark that property. Let's say int property is called x, so you have an int x. You have say the getter is x, the setter is set x, and then the new thing here is the bindable tag, where you say this is bindable x, which gives you basically the binding information. The storage is implemented through the QObject bindable property macro, where you have to repeat the class name, but then you say the type and the name of what you stored. This can be in QObject, or for Qt, our classes it's often in QObject private. And then things look pretty much standard. A getter, which returns the data, a setter, where you set it up, and a bindable interface, where you return basically just in a point, or you dereference the data. Everything else we take care of magically. And if you now want to create a binding on X, you say just my object bindable X set binding, and then you put in the lambda that you want to have. So it's relatively easy to use and a nice continuation and extension of the existing property system from Qt5. Okay, let's move on. Next topic, metatype and variant. This is something where we've also done a lot of work. QMetatype and QVariant were in Qt5 basically serving similar purposes, metatype being the low-level API and QVariant a little bit more the high-level thing where you could store something that has different types. The problem was that the implementations weren't unified. You could not use QMetatype to modify many of the built-in types that we supported in QVariant. So QMetatype was only there to support user types, not the built-in types that we have. We've changed that architecturally now, so that metatype now supports all the types that you can store in a QVariant, whether they're built-in or user types. We're using the same implementation and the same things behind the scenes there. It's all going through QMetatype to handle it. This has a couple of advantages, that we have a higher performance, fast code path. QMetatype only contains now one pointer to a handler struct that basically lets metatype know how to basically construct certain objects, destruct them, copy them, or do other things with them. The registration is much more automatic than you have in Qt5. You, in most cases, don't need the qdeclare metatype macro anymore. And we added automatic support for comparisons and QDataStream into that. Finally, what we did is we deprecated the integer-based type ID that you have been using quite a lot in Qt5, both for QVariant and for metatype. Rather, just use QMetatype directly. Easier, and it's also faster. This is how it looks implementation-wise. We have a QMetatype interface, which basically contains the information about the type, size, alignment, the name, constructor, function, destructor, and so on. And QMetatype basically is just a pointer to that interface. And then the methods that access things basically just call things on that interface. That's as fast as we can get and as convenient as we can make it. Lots of template magic behind it to make all of this work. I won't go into the details there now. Feel free to have a look also there in our source code. QVariant is then built completely on top of metatype. It doesn't really have logic of its own anymore. It just contains a metatype and space to store the data. And what it does basically is for all its operation is it refers those to QMetatype. So for example, the equality operator with another variant, it checks whether the metatypes are equal, and if they're equal, then it also asks QMetatype to compare the data in there. Very simple and straightforward, and that basically gave us a very consistent handling there of those things and made things work, removed one of those big architectural problems that we've had in Qt 5. We also had in Qt 5 already to some extent some sort of generic container interface that would allow you to introspect containers stored in QVariant. So you could iterate over those containers and inspect all the values that were stored in that container. In Qt6, we've extended that support so that you can also modify those stored containers. So here's one example. For example, for a sequential container, we have a QList of dates and we store that in a variant. Now, using the view function, you can actually get an iterable out of that that allows you to iterate over that container and actually also modify it. And it'll modify the container stored inside that variant. So you could, for example, here's an example where you say, oh, we have a list of dates, and if that date falls onto a Sunday, actually I want to move it one day further to the Monday because I don't want to do anything on Sundays. Something you can easily do now in Qt 6, and that was not possible in Qt 5 before. The mock has also gotten quite a lot of improvements. We are now using the new work that we've done in QMetatype to store and resolve metatype information at compile time. In Qt 5, in most cases, we had to resort to string lookups for the type information. Storing the metatype directly is much faster and more efficient and requires a lot less work at runtime to resolve things. So that makes all our mock-generated code faster and more efficient. And finally, we've also in mock added support for bindable properties. I talked about the QProperty macro extension a little bit earlier, which allows you to dynamically now add and remove bindings also through QMetaProperty. Let me get to one last topic that I wanted to talk about. That's not directly Qt core, but that's very much related, and that's that we've rewritten Qt Concurrent. Qt Concurrent has been around for a long time, but has, during the lifetime of Qt 5, not received a whole lot of changes and updates. Now with Qt 6, we took a big step backwards and really looked at Concurrent and looked at how we could make that much more usable for you. Concurrent has now gained a lot of support that make multi-threaded computing much, much easier. We've added support for chaining of computations using QFuture then. You can easily attach failure and cancellation handlers. You can convert actually signals to QFuture objects so that you can do stuff with them. Once the signal gets emitted, you can actually trigger a chain of computations, asynchronous computations, very easily. Added the QPromise class and support for custom thread pools. Just to show you one example, here's a simple example, for example, how you can do some asynchronous work very easily. Let's say you have some data that you want to download from the internet and convert to an image and show that. So we have a download method, takes the URL, a load image method that takes the data, returns the image, and then finally a method that shows the image. Using Qt Concurrent, you can convert all of that into one future. So in Qt Concurrent run the download, and then once that's done, using the then method, you load the image, and then you show the image. And then we can also add very easily an error handler using the onFailed method. So if there was a network error, you can handle that easily there. Can go also one step further using the QFuture Connect to convert a signal. So you can say, I have a network reply that I'm getting, and once the reply emits the finished signal, actually then you start triggering a certain chain of events using QFuture. So then, you read the data from the reply, and then you load the image, and here's a small thing there to move that asynchronously into a new thread. You use the QFuture launch async flag, and then you show it, and the rest moves on like it was before. So that's a very nice improvement that we're having there also in terms of how you do concurrent computing using Qt6. With that, I'd like to conclude my talk. Thank you very much for listening, and please enjoy the rest of the conference.